let me make a few remarks about K1. So firstly, two matrices A and B represent the same class in K1 if and only if we can write A equals B multiplied by some product of elementary matrices. So this is straight from the definition. The group operation in the general linear group is matrix multiplication, but we can show that this is actually equivalent to block addition. So block addition is where we just write A in the top left and then B in the bottom right. This induces the same operation. So why is this? Well, if we just have our normal matrix multiplication, A times B like this, we can stabilize, and then we can write this as the block addition of A with B multiplied by this matrix. But we already saw that this matrix is trivial in K1 because it can be written as a product of elementary matrices. So these have the same class, so we get the same group operation. The third and final remark is if you have an element in K1 and you want to decide whether it's trivial or not, this is much like asking the question of whether a Euclidean algorithm exists to diagonalize the matrix over the ring. So So, for example, we saw we can always do this over the integers to get plus or minus 1 down the diagonal. This is what we saw last time with the s-cobordism theorem. So this tells us that if our ring is the integers, then every invertible integer matrix can be diagonalized to get plus or minus 1 down the diagonal. So this actually tells us that k1 of the integers is z mod 2. Well, if we know that this matrix is trivial because we've got -1 and -1 inverse here, and we saw that this is trivial in k1. Oh wait, hold on, this does. So we can always, if we've got different signs down the diagonal, we can always we can work our way up, multiplying by this matrix to shift any -1 down here, such that the class of the entire matrix is just determined by one entry, and this will then either be plus or -1. So if you had something like, I don't know, this, you just multiply by this on this part, and that gives you just -1 stabilized, if you see what I mean. So then you just get z mod 2. But whether this was plus or -1, we already saw doesn't matter for the s-cobordism theorem, because we can change orientation. So actually we only really care about k1 of z quotiented out by plus or -1, and this is called reduced k1. So with the s-cobordism theorem, changing the orientation of handles so we only really care about and this is trivial. So now let's think about the more general case where we have a fundamental group. So in general, we had our chains generated by the k handles, but with z pi 1 modules, as z pi 1 modules. Now, and then we had, if we take the homology of this chain, this was the homology of the universal covers with z coefficients. Now, in the general case, again we can change the orientation of our handles. This allows us to change -1 into +1, but also we can choose a different lift of our generators to the universal cover, and this allows us to change by any group element in pi 1 of m. So by changing orientation and choice of lift, I'll finish writing this on the left. So by changing orientation and choice of lift, we can, if we have our boundary map, which looks something like just plus or minus group elements down the diagonal, then we can change this to the identity matrix by changing these choices we've made. So this motivates the definition of the Whitehead group. And when we have a boundary map which can't be made into one of this form, this then generally can't be made into the identity matrix, and we have a genuine obstruction to our s-cobordism being a product. Okay, so quickly a couple of examples. We already saw that reduced K1 of the integers was 0, so we get the Whitehead group is also 0. It turns out that the Whitehead group of fundamental group of a surface is also 0. Whether either orientable or non. And well, have a look at Andrew's book for reference for that. And also in Andrew's book for the Whitehead-Novikov conjecture. Which I should really say more about, but I'm not going to. Again, look in the book.